Hello and welcome to Algebra 2 tutorial. With this video we're going to keep taking a look at systems of equations, but this time we're going above and beyond, and instead of having two equations we're going to have three different equations. And when we have three equations, it's actually going to be three variable equation systems. So we're going to have an x and a y, but we're also going to have a z. And this actually makes us work in three dimensions instead of just two. And so we're going to take a look at three examples here. The first one, just like with two variable systems, we're going to look at graphing, a graphical representation. Now this gives us a good visual, but it's not actually something you can do by hand because it is three-dimensional. So first, let's get a view of what this looks like. I've got a website here we are going to go to see this. So when you graph a three-dimensional equation with three variables, x, y, and z, you get what's called a plane. And so this green sheet of paper almost is a plane. And it's in three-dimensional space, so I can move it around. And you can see it's a flat piece of paper just about. And we call that a plane. So there I can flatten it out. You can see it is only two dimensions. And then what we do is we take three of these and graph them together. So here's the first one that's been graphed. Here's another one. It's another sheet of paper, and you can see these two sheets of paper do intersect. Let me get a good view here. Right here, they intersect along that line. And then we do a third one, which will be another sheet of paper. It also intersects the other two. But what we're interested in is where the three pieces of paper intersect at the exact same spot. So if I move it around, after a little while you can see that all three sheets of paper, red, blue, and green, are right here at that one spot. Along this line right here we have red and blue. If I move this around, you can see in here we have sort of green and blue. Up here is just red and green along this line, and all of those lines converge right about here where you have all three pieces of paper in one spot. And I can even highlight that right there. It's at the point 4, -3, +3. So now we have an x and a y, but also now a z. Gives us a point in three-dimensional space, which you can see is why you can't really do this by hand. There's no way you could draw that by hand. But it gives you a pretty good visual of what we are going to do. We are going to be trying to algebraically find these three numbers, the x, the y, and the z. Now when we do that, there's a couple of different options of what could happen. Here are those three options. The first, if you graph the three equations, you could get three sheets of paper that are in a sense parallel. They don't intersect at all. That would be no solution. You could get the three sheets of paper intersecting and where they all come together in only one point. That would give you one solution. A third option, over here on the right, is if the three sheets of paper intersect in such a way that they share an entire line, and then you'd have an entire line, an infinite number of solutions. So that kind of gives you a visual of what this means to solve a three-variable system. So the graphic gives us a good view, but we can't actually do that by hand because we can't draw in three dimensions. So let's do this algebraically. So here we have three equations, and each equation has an x, a y, and a z. So you can imagine there are three pieces of paper in three-dimensional space, three planes. We can't visualize it, but we can algebraically figure out where those three planes are in the same place, where they all intersect together. It's a little difficult, but we should be able to make this work. And what we're going to do is use elimination. Our strategy for solving a two-variable system. And we're going to try to make some variables eliminate. So that's the first thing we look for. How can I make some of these variables eliminate? And so I think on this one I will pick the z's, because I can take this z, the negative z, and make it eliminate this 2z pretty easily, and then I can make it eliminate this 5z pretty easily as well. So first let's make it eliminate the 2z. In order for that to happen, I need this to be a 2 in front of the z. So what we'll do is we'll take this equation and multiply it by 2. That way this has a 2 in front and it will cancel out that 2. So what that will become is, let's see, distribute, we'll get 6x plus 2y minus 2z is equal to 6. And I'm going to compare it to this one here, so I'm just going to rewrite it right underneath it so I can see them right next to each other. Is equal to negative 16. We can now combine these two, and we will get 6x and 2x makes 8x. 2y and negative 3y makes negative 1y. The z's cancel out. And 6 and negative 16 makes negative 10. So I did that once. Now I'm going to do that again. But this time I'm going to make it cancel out the other equation, the 5. So this time I'm going to multiply by something else. This time I'm going to multiply by 5. So I'm going to write this over here. So now 5 times 3x is 15x. 5 times y is plus 5y minus 5z is equal to 15. And I'm going to rewrite the top equation right underneath it because those are the two I'm comparing. So x plus 2y plus 5z is equal to negative 17. And so now I'm going to combine these two. 15x and x is 16x. 5y and 2y is 7y. The z's cancel out. 15 and negative 17 is negative 2. So now we've simplified this a bit. These two red equations have two equations with just x and y. I should be able to solve those just like we used to. So let me write the other one underneath here. 16x plus 7y is equal to negative 2. All right, now this looks just like an easy two-variable system that we can solve. It's going to take a few steps, but it shouldn't be too hard. Let's see, I think what I'm going to do is multiply the top one by negative 2. And if I multiply the top one by negative 2, this 8 will become a negative 16 and cancel that out. So I'll write it right underneath. Negative 16x plus 2y is equal to positive 20. I can now combine these two. The 16x's go away. 7y and 2y is 9y is equal to 20, and negative 2 is 18. And that goes pretty easily. Y is equal to 2. Now, I know what you're thinking. That was a crazy long and hard process, and it was. But we're basically done. Once you find one answer, all the others should be pretty easy. The hard work is done. We just got to take this y equals 2 and plug it in somewhere so we can solve for everything else. And so I'd say I've got this equation over here. I'm going to plug it in over here. Once I know what y is, x is the only variable, I can figure out x. So 16x plus 7 times y is 2, so that will be 14, is equal to negative 2. Minus 14 to both sides. That goes away. 16x is equal to negative 16. And divide by 16, x is equal to negative 1. As you can see, that was pretty easy to get x. So now we have x, we have y, we have one more variable to solve for, a z. And so we can choose any 3 of these to plug this into. I'm going to choose the top one just because it's on top and I can get to it easily. So x in front is a -1 plus 2y, so 2 times the y, which is another 2, gives us 4, plus 5z is equal to -17. Let's simplify this. That becomes a 3. Subtract the 3 over. And then on the other side, we get -20. Divide both sides by 5, and z is equal to -4. So we have 3 answers, the x, the y, and the z. We should probably put that in the form of a point. So the x goes first, -1. The y goes second, 2. And then z is -4. So that is a point in 3-dimensional space where all 3 of those planes, those sheets of paper, are intersecting at just that one point. So it's pretty long. But the first part is the hardest. Once you get your first answer, the other answers are pretty easy because you just keep plugging things in. All right. That's our first example. We're going to do one more to show you how things can get a little weird and maybe not work out. So example 1 worked out just perfectly. That's as long as it can get if you have an actual answer. Example 2, it's not going to quite work out the way we want it to. So, but we're still going to start out the same because we don't know that. We're going to take a look at our numbers and think which ones can we eliminate the easiest. And so I think I might choose to eliminate the x's because I can take this 2 and turn it into a 4 pretty easily and then make those 2 eliminate. And I can make this 4 into an 8 pretty easily and make those 2 eliminate. And I think that'll be my best plan of attack. So first I'm going to take this one and multiply it times 2. So that will give me a 4x and a -8y plus 2z is equal to 6. And then we're going to compare that to the -4x, the bottom one, plus y minus 2z is equal to -14. I'm going to combine those two together. The x's go away. -8y and 7y and positive y is -7y's. And here's where something a little weird happens. The z's also cancel out. 2z and -2z go away, so I'm left with that is equal to 6 and -14 make -8. And so now I have an equation with only one variable. Well, I might as well solve that. Divide both sides by 7. Y is apparently equal to 8/7. And the fact that that happened is a little fishy. And so I'm a little nervous about that. But let's keep going with our plan. Our next plan was to combine these two to make those go away. In order to do that, I need to take this one and multiply it times 2. That means this will become an 8, and these will then cancel out. Let's take a different color this time. So I'm going to write the top one first. 8x minus 2y plus 4z is equal to 7. And now I'm going to multiply the bottom out and see what we get. So 2 times -4 is -8x. 2 times y is 2y. And 2 times -2z is -4z, which equals 14 times 2 is -28. All right, so now we're going to combine these two. 8x and -8x go away. -2y and 2y go away. 4z and negative 4z go away. So if all that goes away, we are left with 0 equals 7 and negative 28. Those combine to make negative 21. And take a look at what we've got left over. 0 is equal to 21. And that is obviously not true. That's a contradiction. False, I guess I could write. And that definitely tells me that this system of equations is not working, and there is no solution here. Now, I don't know exactly what the graphs look like still, but I do know that these three planes, whatever they look like, they do not all cross. They do not intersect at one specific point. It's possible that some of them don't intersect at all. And so we just say there is no solution here. All right. A little bit less algebra, actually, when things don't work out, thankfully. But we had a good look at three variable systems. Hopefully you see a good graphical representation of it. It is three planes intersecting in three-dimensional space. We had a good example where all the numbers worked out nicely. It's kind of long, but the numbers do work. And one example where the numbers didn't work out and we had no solution. So why don't you try one for practice as well? There's one with different numbers. Try to make things eliminate and find the solution.